Our next topic is weak acids and bases. In the last section, 16.5, we talked about strong acids and bases. And the definition of a strong acid or a strong base was that it reacts with water completely, or it dissociates completely in water, which means that when we write a chemical reaction for a strong acid or a strong base, we use forward arrows. We also said in that section, but we didn't focus on it very much, a weak acid or a weak base they do not completely react in water or with water. Instead, they exist in equilibrium. And we did look at a couple of examples, one example of a weak acid and one example of a weak base in equilibrium with water. Let's look at another example. Let's say H2CO3. This is an acid, carbonic acid. And I'm going to put some states on this, aqueous. And it reacts with water, which is a liquid. But since carbonic acid, H2CO3, it's not one of our 6 or 7 strong acids, that means it's a weak acid. So it is in equilibrium with water, and it produces HCO3 minus, which is aqueous, and H3O plus, which is aqueous. And we can write an equilibrium expression for this weak acid in water. We can write an equilibrium expression for this reaction right here. Remember, equilibrium expressions are capital K, and they are products over reactants raised to their stoichiometric coefficients, leaving out pure solids and leaving out pure liquids. So for this reaction, our equilibrium expression is HCO3 minus times H3O plus over H2CO3. We're leaving out H2O liquid because it's a liquid. We leave out pure liquids. And this particular equilibrium expression, because it applies to the reaction of an acid, H2CO3, we're going to call this a Ka. Kind of like we had Kw, an equilibrium expression for water. Ka is the equilibrium expression for an acid. So what we want to be able to do with weak acids and weak bases is find a way to easily calculate the pH of the weak acid or base. Let's look at an example of this type of problem. What is the pH of 0.075 molar CH3COOH? The Ka for that compound, CH3COOH, the equilibrium constant, is 1.8 times 10 to the minus 5. So what is the pH of this solution? Now, in section 16.5, we talked about how to calculate the pH for a strong acid or a strong base. And we said, first of all, we have to remember that the pH is the negative log of the H3O plus ion. And so in order to calculate the pH, we need to know the concentration of H3O plus. For a strong acid or a strong base, we made some ice tables, but mostly what we learned was that the H3O plus concentration was going to be equal to the concentration of the strong acid or the strong base, unless it had like 2 OH groups, we saw that, then it was different. But for the most part, for a strong acid, we could just plug in the concentration of the acid, the molarity of the acid, plug that right into the pH equation, and we get the pH. That's not going to work for a weak acid, and let's take a look at why. So to solve this type of question, the first thing that you need to do, step one, is going to be to write a balanced equation. And this is going to be because we're going to ultimately need an ice table for this. So we need to have a balanced equation. And we're going to have to come up with this equation on our own. The reactant, one of the reactants in this balanced equation is always going to be the acid that's given to us in the problem. So the CH3COOH, that's just coming from the problem. The other reactant is always water, every single time. Whether we're talking about an acid or a base, the second reactant is always water. And then you have your products, and this is where you're going to have to figure out what the products are. If this reaction is for an acid, one of the products will always be H3O+. How will you know if this reaction is for an acid? Ka. When you are given a Ka, that A means that you have an acid. And when you have an acid, you're always producing H3O+. So where did the H3O+ come from? It came from the acid, CH3COOH, moving one of its hydrogens over to water. So the other product of this reaction is CH3COO-. It's lost one of its hydrogens. So step one is to write a balanced equation. Step two is going to be to make the ice table. So this is going to be our step two, ice table. Now we know how to make ice tables. We've practiced them quite a bit. We're going to start with the initial amounts of all of these things, and the problem tells us initially we have 0.075 molar acid, and initially we don't have any products at all, and we do have an initial amount of water, but we're going to ignore water completely, just like we did with the strong bases. The change, this is how much acid is being reacted and how much H3O+ is being formed and how much CH3COO- is being formed. When this was a strong acid, we said because it's a strong acid, it's going to totally react. All of this stuff is going to go away. That's the definition of a strong acid. But this is a weak acid, so it's not going to react completely. We don't know how much of it is going to react. We know some of it will react. We know it's going to be less than 0.075 because we know it won't all react, but it's somewhere in between 0 and 0.075, but we have no idea what it is. It's an unknown, and so we're going to call it X because we don't know what it is. What we do know, though, is however much CH3COOH, however much of that we react, that is how much H3O+ we've made, and it's also how much CH3COO- we've made. How do we know that? We know that from the stoichiometry of the balanced equation. Everything is 1 to 1 to 1 here. So if we are reacting minus X of our reactant, then we are making plus X and plus X of each of our products. So at the end, when this is all over, at equilibrium, we have 0.075 minus X, we have X H3O+, and we have X CH3COO-. Let's not forget, our goal here is to calculate the pH. We need to know what X is, because pH is the negative log of the H3O+. And the H3O plus is our X. So how are we going to get X? What we need to do is go back to our equilibrium expression. So this is going to be our step 3. Write an equilibrium expression. The equilibrium expression is going to be a Ka. Again, we know that it's a Ka because the problem told us this is a Ka. It's a Ka. We actually know the value of the constant, 1.8 times 10 to the minus 5. And for this particular reaction, it is products, H3O plus and CH3COO minus over the reactant CH3COOH. Let's plug in from the equilibrium expression the stuff that we have at the end of the reaction. Plug that into our equilibrium expression. So we're going to get 1.8 times 10 to the minus 5 equals X, our H3O plus value, we don't know what it is yet, and X, our CH3COO minus value, over 7.5 minus X, or 0.075 minus X, which is our CH3COOH value. So all we have to do is do some math here and simplify this and solve this problem. Now this problem, maybe depending on how much you like math, when you look at it, it might look easy, it might look complicated. It's actually pretty simple, but it is a quadratic. It's going to work out to be a quadratic, so you're going to have to use a quadratic solver to solve for X, and that's not hard to do because most calculators will just do that automatically, or you can use the internet to do it for you. But we don't have to do that. We can make this problem even easier. We can simplify this with an assumption or approximation. So we're going to add that in as our step 4. Let's use an assumption, and the assumption that we are going to use is that X is very small. We're making this assumption in part because we're looking at the value of Ka, and Ka is a really small number. 1.8 times 10 to the minus 5 means that this reaction really doesn't like to work. It doesn't like to move forward. The amount of CH3COOH that's reacting is a really small number. So when we actually subtract X from 0.075, and we do, round it back to the correct number of significant figures, we're just going to end up with 0.0075. X is such a small number that when we subtract it from 0.075, it doesn't change the value at all. Now that might be kind of blowing your mind a little bit, but trust me, let's move forward, and then we're going to come back once we solve for X and see how valid this assumption actually is. So we're going to make the assumption that X is really small, and when we make that assumption, our equilibrium expression gets much easier to solve. And let's actually, up in our equilibrium, in our ice table, let's write this approximation in. 0.075 minus X is approximately equal to just 0.075. Once we get the problem like this, it becomes a whole lot easier to solve. And to solve for X, we have 1.8 times 10 to the minus 5 times 0.075, and that is equal to X squared. And I'm getting my calculator out. 1.8 times 10 to the minus 5 times 0.075, and we're going to take the square root of that number. X is 0.00116. Now, before we move forward, let's think about the assumption that we made, that x is very small. And let's find out if this is true. Is this true? Was that an okay assumption for us to make? Let's try. 0.075 minus the value of x that we came up with, 0.0016. Let's see what that actually equals. .0734. Not exactly the same. But it's close enough for us. Now, if you go on in chemistry and this becomes important, then you're going to need to not make assumptions like that. But for this level of chemistry, for this class, this is a very reasonable assumption for us to make. So we have solved for x. We've got a value of x. And let's remember, in our ICE table, the value of x, let's erase some of these marks. The value of x is what we want to plug into the pH equation. The value of x is the value of the H3O+. pH is the negative log of 0.00116. And that works out to be 2.94.